there, so this comes natural to me. I'm going to pass it around for starters as I'm talking. An example of a stone that was plucked when I was here working with Jeff at O'Brien. I picked up one single oiled stone as an example and took it back to my lab. I have the data that I can email to any of you, but this stone was given a single light application of CytoSol, somewhat analogous to what we'll be doing this morning, and then was waited 15 minutes. We just gave it a simple wipe with a paper towel. This is a stained stone, but it's no longer wet with oil. It probably is not releasing that many polyaromatics and hydrocarbons to the environment. And if you smell it, it no longer can smell the petroleum. So I'll just pass that around. Same with a stick. This is a piece of driftwood I left somewhere of the original oil. This was a stick that I jabbed into the oil. It was clustered with oil. We put a light spray. In this case, I did it with a containment. I collected the cytosol and applied it a couple of times, so I've got several applications. Wiped it off with a paper towel. It is not clean, but it's a lot better than it was. Obviously, it's a porous material. The purpose of the experiment this morning is to do a very simple demonstration of how the cytosol would dissolve this same type of fuel oil. I have a piece from the rocks here. Dissolve it, and then what I'd like to do is use the opportunity to show you what happens when it's exposed to water. A key component of our technology is the use of water to lift and float. I borrowed that term 10.5 years ago from Jackie Michelle when I was at one of the oil school conferences. Lift and float means that the polar solvent, not dispersant, it's a polar solvent. It has two oxygen molecules and a long hydrocarbon tail. If you remember your biology, it's very much like a phospholipid. It's a molecule that wants to interact with water only in one way, and then the tail portion goes back. Now, if you remember, a fatty acid or a detergent is the same molecule. Typically, Dawn detergent, which is made from soybean oil as well. Dawn detergent is C18 carbons, and then it has one oxygen on a double bond, and it has a single oxygen as a fatty acid. In other words, it's a O-. That O- allows that molecule to coalesce into a round spherical structure that we call a micelle. The micelle has all those little fatty acid, the oxygens pointing outside, and that dissolves into water. That is also a component of any surfactant, including what's in correxit. This molecule lacks the O-. That oxygen is now covered by a methyl group, CH3, and that methyl group makes it a polar, non-ionic solvent. It's not a detergent. It cannot disperse in the water. It will not form a micelle. There is no critical micellar concentration to deal with. The solubility of our product, if you poured it in the bay and let it come to equilibrium at 20 degrees, we've done that several times, is about 14 to 16 parts per million. So it's a low solubility dissolved in cool bay water, but it likes to float up, and because of that polar nature, it does tend to form a structure that I call them globules. Jim Bonner called them pancakes. You'll see them in just a moment. The oil cytosol mixture forms these little puddles that are about 1 or 2 millimeters deep. And I'm hoping today, despite the blasting of the pressure wash, we'll see particles of oil cytosol coalesce and form these little pancakes out there, and then you'll see how quickly they absorb. I say quickly because now we've changed the viscosity, of course, but we've also removed the adhesiveness of the crude oil. That fuel oil is no longer tacky once it's exposed to cytosol, and it now wants to penetrate into absorbent boom. It will not stick, however, to the typical pom-pom polypropylene type of a device for absorbing based on adhesion. So our methods of collection have to be either skimmers, like a Weir skimmer, or it has to be by absorption. So let's get on with the experiment. This is the sample of tarred oil.
Can I give you one? Oh, yeah.
Which is very much like a pitch. It's like roofing tar.
Which oil is this? Our oil?
This is, yeah, I collected this with O'Brien the other day.
Okay.
Just trying to get enough of it. So I may have to just walk around. You've all seen it from a distance, but just to remind you, it's just tarry. Notice it's wet. A lot of the oil we're going to see on this experiment out in the water is not wet. It's already been oxidized and volatilized and dried in the sun. But this is an example of wet, and there are some pockets still like this. What I'm going to do is really rough and basic. I'm going to just put this into a container and proceed to apply some cytosol just so you can see what happens to it.
get a picture of that before you do it.
Sure. Could I have a volunteer hand to just hold a, who's not holding the camera? Jeff,
Yeah.
would you just hold that for me? That'll give me 2 hands, thank you. Let's stand over our, this is so viscous, I can't even get it out of here. Yeah. So viscosity is obviously important. One of the things that happens, as we all know, to fuel oil is it begins to oxidize, cross-link, evaporate. A lot of the components go away, and you are left with a tacky, heavy material that's not very mobile, and therefore difficult to collect. The premise on which we developed the CytoSol technology was that if we could liberate this horrible material from surfaces of rocks or marshes or plants and get it floating on the water, then it would have a chance to...